Hey everyone, I hope all of you that are in Cambridge have had a chance to enjoy the good weather, or that, hopefully wherever you are, that spring is on the way. And so today we're going to be talking about the paper Attention is All You Need, which has been an enormously influential paper in NLP. And so before we get into the details of how that paper works, I just want to start by recapping attention, which we introduced last class in the context of a model called seek-to-seek that's used for machine translation. So if you guys recall, we had this architecture shown here, which takes in a sequence and puts out a sequence of words, hence the name seek-to-seek. And the challenge of just the vanilla version of that model is that the only information that it received from the encoder was the information contained in that final encoder hidden state, which got passed to the decoder. And so any information from earlier in the sequence would have to be passed along to that hidden state, which led to this kind of bottleneck and made it difficult to capture information from earlier in the sequence. And so in this example, it's translating a phrase from French to English. And essentially the decoder is a language model that generates the target sentence conditioned on that final encoding. But what we did with attention is to at each part of the decoder to use a direct connection to the encoder to focus on a specific part of that source sentence. And that effectively allowed us to pass information from a variably sized encoder model to a decoder in a way that's learnable, because we don't know the size of that that encoder model ex ante, because it depends on the length of the sentence that we want to pass in. And as we talked about, and as we're going to see more this week, this idea of attention has transformed NLP. And so in the first incarnation of attention that we saw last class, just to recap, we starting with the first hidden state of the decoder, it gets passed a start token, which tells us to start translating the sentence. And we take the dot product between that first encoder hidden state and that decoder hidden state and the first hidden state of the encoder. And that gives us a number, which is called the attention score. And then we do that with each of the positions, take the dot product between the encoder hidden state for the second position and the decoder, and do that for the third word and the fourth word. And so now we have these 4 attention scores, which effectively give us the attention distribution. We take those, softmax them to get probabilities, and then we multiply each of those encoder hidden states by the probability from that softmax to give us the attention output. And we concatenate the attention output with the first decoder hidden state, and that which comes from the encoder and the start token, and that gives us the first word of the sentence. And then we just repeat this with each word of the sentence. And so we now see with the second word, which is going to predict the word poor, it's attending, to the right place, to the place that we would expect, the equivalent of that word in French. And then, we keep on going through, and for each token, each hidden state of the decoder, which is predicting a different word in the sentence, it's attending to different hidden states for the input sentence. And we keep going until we reach an end token. And if you look at that kind of attention distribution at the elements that it's paying the most attention to, it's essentially giving us the alignment. between those sentences that we're translating, the target sentence and the source sentence. And it does this without us having to give it any data on alignment. It learns this just through seeing the translation pairs. So this solves the bottleneck problem. And another important advantage that we saw was that it helps solve the vanishing gradients problem by providing a connection to faraway states. And this is kind of a recurring theme of this course when it comes to discussing major advances in the literature. And it goes back to the fact that at its core, deep learning is just linear algebra and multivariable calculus. And so if we want to transmit information from states that are far away in the network, when we backprop, we're just using the chain rule multiplication, right? And we need those direct connections because if you multiply a bunch of numbers that are less than 1 together, you're going to get a 0, right? And so we need those sort of those direct connections to faraway states if we want the model to be able to attend to that. But this is something that we've seen kind of over and over again in the course. And so more generally, the definition of attention is that given a set of vector values and a query, attention computes a weighted sum of the values that is dependent on the query. The query tells us where to focus in creating a weighted sum of the values. And so in short, attention creates a fixed size representation of an arbitrary size set of representations given the query, which is itself a representation. Okay, so we concluded by saying a little bit about attention variance. So suppose that we have a set of values, which in the example we just saw were our encoder states, and a query Q, which in the example we just saw is our first decoder hidden state. Attention always requires computing an attention output A from the attention scores, which is going to be just the weighted sum of the values, where they're weighted by, this output from the softmax. But there's different ways to compute those attention scores, which here are denoted by E. And so there's dot product attention, which is what we just saw, which works, but you need the dimensions of your query and your values to be the same. You can also do multiplicative attention, in which case, you no longer need those dimensions to be the same. They're reflected in the weight matrix. And there's also something called additive attention. Okay, so that's a recap of kind of the original version of attention, which we discussed in the context of seek-to-seek last class. Are there any questions at all about that? Okay, and so now I'm going to move on to talking about the transformer model. Okay, so first to just give an overview, then the transformer is a seek-to-seek model that is based entirely on attention, and hence the name of the paper is Attention is All You Need. And so this is the figure from the paper that shows the architecture, and hopefully kind of by the end of the lecture, you'll have a good understanding of what is going on with this architecture. And so the paper has been enormously influential in natural language processing. People will call it, the ImageNet or the AlexNet moment of NLP. Kind of analogous to, the AlexNet paper that kickstarted the whole deep learning revolution. So the original transformer is about machine translation. And so when we presented today, it's again, going to be in the context of doing machine translation. And, it was a paper written by people at Google who were working on, improving Google Translate. But we will see, on Wednesday that the basis for many different NLP model architectures. And kind of it's hard to do anything, I think, in NLP today that is not, using the transformer in some ways, as it's kind of the core of just about any modern language model. And we use modern language models in turn to do kind of any downstream task that you might be interested in, whether it's sentiment analysis, classification, more generally named entity recognition, query, summarization, kind of all those downstream things. You need representations, and essentially the way those representations are created today in NLP is through some variant of the transformer. And so one great thing about the fact that this is such an influential paper is that there are a lot of efforts to explain it, some of which are very good. And so I'll use various visualizations today from a blog post called The Illustrated Transformer, which is probably like the most famous explanation of the transformer. And you guys can also go kind of check that out and ponder it at your own leisure. But in addition to kind of just explaining the model and like the technical details of what's in it, I want to draw your attention to parts of it that are going to be important for understanding how the transformer has been integrated into language modeling. And so on Wednesday, we will discuss sort of the various modern language models that are based upon the transformer, and they use it in different ways. And if you get into NLP, you'll see the names of these models like constantly used and thrown around. And when you want to do your own downstream task, like you're going to have to decide which one of them you want to use. Do I want to use BERT, Roberta, like, XLNet, like, there's a whole range of them, and we'll be introducing them. And they kind of use the transformer in different ways, and they're also they're trained on different data. They maybe have different training objectives. And like, yeah, if you do any NLP task, you're going to have to make a decision about which of these models to use. And in order to understand how they're different, it's important to understand how they use the transformer in different ways. And so this is kind of essentially a basis for that. So, you can not care one bit about machine translation, which was the original application. But if you kind of want to do something, using modern NLP methods, you're almost certainly, going to be using, representations that were trained with a model that used the transformer architecture in kind of various different ways. And so that's why we need to understand this. And I'll try to highlight kind of the aspects of it that are going to turn out to be important in Wednesday's lecture. Okay. And so specifically the paper, it like simultaneously kind of made a lot of advances in how we specify attention, and these will all kind of come up at various points as we describe what the model does. And so most fundamentally, it introduced the idea of self-attention, which we're going to spend a while talking about what that means. It introduced multi-headed attention, something called positional encodings, normalized dot product attention. And so it's a really kind of, remarkable paper in the sense that it kind of simultaneously made these various advances that, by now I think the paper was like 2017, and this is still kind of like the state of the art. And people have tweaked various things about how the transformer works, but essentially these are kind of very powerful ideas in terms of how to create a computable representation from text data. So just the highest level overview. And so, as I said, the transformer was developed for machine translation. and hence it has an encoder component and a decoder component, like just like the models that we saw last class. And in the machine translation context, that you put in a sentence in French and it outputs a sentence in English. And again, this was really, the model was developed by people at, Google Brain and Google Research who were trying to make Google Translate work better. But having an encoder and a decoder is not essential to the transformer architecture. So as we're going to see next class, many of the most powerful applications of the transformer use only the encoder blocks or only the decoder blocks. And the encoder and decoder work a bit differently in ways that we're going to discuss. And this is going to be important for understanding language modeling, because some language models use only encoder blocks and others use only decoder blocks. So we'll talk about how the encoder and the decoder are different, right? Because in a language model, you only need one of those. You're not encoding and decoding something, you're just encoding it, or you're just taking a sequence and computing numerical representations, and that's your language model. Whereas in translation, you take a sequence of words, you create numerical representations, and then you have to turn those representations back into another sequence of words, like in a different language. Whereas when we use the transformer to build language models, we just need kind of one side of that, because we're just taking text and turning it into representation. We're not, outputting text. But this kind of the architecture that you see in the transformer, where you input a sequence and output a sequence, that is relevant kind of for downstream tasks, like for summarization. That would be relevant. And so, this idea that this became very powerful, and kind of revolutionized NLP in general, with people just using kind of the encoder blocks or just using the decoder blocks, goes back to the idea that we can think of neural networks as Legos that can be stacked in kind of various different ways. We have to, take care that, like, we don't have a vanishing gradient problem and, things like that. But if we get the architecture, right, essentially, we can take different components of things and stack them in different ways. And that, again, is like one of the most powerful kind of ideas of this course. Okay, and so in the transformer paper, there's a stack of 6 encoder blocks and a stack of 6 decoder blocks. So there's nothing inherent about stacking 6 of these blocks. This is just a choice. And, as we saw kind of in talking about CNNs, that subject, to solving the vanishing gradient problem, the more blocks that you stack, kind of the better your model should be, because, at worst, it should be able to learn an identity representation, and at best, it's, getting better. And so, for example, we'll mention a model on Wednesday, a language model, which is called GPT-3, and it stacks 96 transformer blocks. So why not always stack 96 transformer blocks? Well, the way that they stack 96 of those blocks, which is just kind of decoder type blocks, that required estimating 175 billion parameters, which cost an estimated like $4.6 million to train. And so this is just like an enormous model, but sort of, it worked. We'll see how this solves the vanishing gradient problem. And so, subject to having the substantial compute, this model was developed by this organization called OpenAI, that's essentially like an affiliate of Microsoft. Subject to having that kind of compute, you can stack 96 of these blocks, and you need an enormous amount of data and an enormous amount of compute to train that. But to train language models, as we've talked about before, you don't need supervised data, you just need to scrape tons and tons of text. So it's possible. Okay. And so the encoder and decoder layers do differ in important ways. They're also similar in important ways. And as I said, you want to pay attention to this, because then when we go to different types of language model architectures next class, some will use an encoder approach and some will use a decoder approach. And so this is what the encoder blocks look like, generally speaking. Each one of them has a self-attention layer, and we're going to talk about what that is, and a feed-forward neural network layer. And we stack 6 of these on top of each other in the original transformer. And they have the same architecture, but they do not share weights. And like there are versions of the transformer, lighter weight, smaller versions of the transformer where these layers can share weights. And those are also kind of popular and something that we'll talk about Wednesday. If you need to, if you want like a lightweight model and you don't have much compute, you can make them share weight. So there's nothing kind of inherent about that, but in general, like the best performance is going to come from models where those layers each estimate their own weights. And actually we should draw the encoder blocks like this. And so in this example, we're just taking a sequence of 2 words, so it's easy to show in a picture. And we look up the embeddings for those words in a lookup table, just like kind of we saw before, and that table itself is full of estimated parameters. And we feed those into the self-attention layer. And, as we'll see in a minute, the whole point of self-attention is that there's dependencies. But then we feed it through the feed-forward layers, and that happens in kind of in parallel. The representation for each kind of word in the sequence is fed independently through the feed-forward layers. And as you can see, like, there's an important parallel aspect, or actually aspects to this. And so if you go back and think about when we discussed RNN, you feed things in as a sequence. You feed in the start token that predicts the first word, and you take that back as the input at the next step that produces the next word. Then that output becomes the input. And you go through the RNN word by word by word. And so that's like a serial computation. You can't parallelize that. And so when you run that, you have to run it in that order, like, one of the great advances with GPU computing is it's really good at just parallelizing like tons of computations. And you can also run things on multiple GPUs. And so in the case of the transformer, you feed in the entire sequence at once. So here, this is like 2 words. When training language models, it's often something like 512, tokens, which are usually, like in that case, subword tokens, but that's kind of a detail. So you're feeding in these longer sequences, and this is not, at least at the encoder stage, this is not like sequential. And so you feed them all in at once to the self-attention layer, and you do a bunch of computes there that we're going to see, and then you get a representation out of that for each word, and you feed them independently through these feed-forward layers. And so the only thing that is kind of like that is serial here is like passing it up through the depth of the stack. And so we have these 6 kind of encoder blocks, but within the blocks, things are parallelized. And that's super important because you can do parallel compute stuff. And that's what makes it possible in the case that we just saw to estimate a model with, I actually forget how many billions of parameters, right? Which you can never do with an RNN. But because you can do so much of this in parallel, if you are Microsoft or Google and you have access to a giant, parallel computing, cluster, you can literally train these models that have billions and billions of parameters. And again, subject to like, getting the architecture right, so you don't have problems with optimization, which like with vanishing gradients, bigger models are going to tend to be better. And so it's going to produce results that are a lot more powerful. Okay, and that's kind of a theme. Parallel computing is a huge thing. Okay, so the decoder blocks also have a self-attention layer and a feed-forward layer, but they include an additional layer sandwiched between those, which is called encoder-decoder attention. And this layer attends to the final encoder state, sort of like what we saw in seek-to-seek earlier. And so that's the first difference, kind of between the decoder and the encoder and the decoder pays attention kind of to the encoder hidden state like we saw before. But another difference that is going to matter a lot when we come to language modeling, when we come to language modeling and we're thinking about just stacking encoder or decoder blocks, if you just stack decoder blocks, you're going to throw out that encoder-decoder attention, right? Because there is, if you have a stack of decoder blocks, there's no encoder to pay attention to. And so the big difference, when we come to transformer-based language models is that self-attention actually works differently in the encoder versus the decoder in a way that's actually very easy to understand. And we will come to this when we discuss how self-attention works in each layer. Okay. And so previously, attention allowed each step of the decoder to attend to different portions of the encoder. And a key insight of the transformer is that we also want a sentence or a sequence of words that we feed in to be able to attend to different portions of itself while it is being embedded. And so the paper uses an example. The animal didn't cross the road because it was too tired, and the animal didn't cross the road because it was too wide. And you'll see that these sentences are essentially the same, except for, kind of the last word in the sentence, but that last word completely changes what it refers to. And so in the first case, it, you guys can probably figure out that it refers to animal because animals can be tired and roads can't. Whereas the second, sentence, it is referring to road because roads can be wide. Animals we don't usually think of as being wide. And this is super important in machine translation because, lots of languages, unlike English, have gendered pronouns. And so you need to know what that noun it's referring to is and what gender it has, or you can't translate it. And this is something that kind of models before the transformer really had a hard time with. And the transformer is able to do a much better job of this through self-attention when it embeds the word it to start with. And the encoder, it's going to be able to attend to, what part of the sentence it should be looking at to decide how to embed that. And so this is showing where the word it is attending to in each of those sentences. And so in the sentence, the animal didn't cross the street because it was too tired. It's attending to, animal. And in the other case, it's gonna attend to street. And so if you think back again to when we talked about RNNs, the hidden state allows the RNN to incorporate past representations into the current representation. And self-attention is what serves this role within the transformer architecture. But as we mentioned, the transformer architecture, the whole thing can be parallelized, which is going to allow you to just have a much bigger, much more kind of powerful model trained on much more data. But essentially, that's the intuition there. This self-attention is doing what hidden states do in the RNN, but now we don't have to pass things in sequence where we're just kind of passing along this hidden state. We can pass everything in at the same time, and then let each word decide where it's going to attend to within the same sequence. And as you'll see, we're going to have something called multi-headed attention, where we have multiple attention heads that we compute, and so we can allow it to kind of refer to different places. And so this is just essentially like a much more powerful architecture, because we're not just trying to capture everything in this hidden state vector, you know, that maybe we do like, you know, a bidirectional LSTM. So we run the sequence forward and capture things in the hidden state and then run it backwards. But essentially we have to capture everything in the hidden state vector. Whereas with self-attention, it's just a much more kind of flexible way to capture those dependencies, and it lets us process everything in parallel, which means that we can fully harness the potential of like GPUs and modern like parallelized computing. And this gave us, you know, impressive results. You know, again, sort of coming from the paper. As I mentioned before, there's this data set called BLUE, which is like the translation benchmark, and kind of blew everyone out of the water. This is like English, German, English, French. This is kind of like true more generally. It just really revolutionized machine translation. And then people realized like this architecture is actually kind of much more broadly applicable. Okay, so before we get into the details of how this works, are there any questions about the overview? Okay, and so we'll start out by talking about how the encoder blocks work, and then we'll move on to the decoder and the final linear and softmax layers, and just say a word about training, which is very straightforward. Okay, and so there's a few key features of the encoder blocks that I am going to highlight. And so kind of the first one, which we've touched on, is encoder self-attention, which means you pass in this sequence of words. So maybe it's a sentence, maybe it's 512 words or more, depending on kind of the size of your model. You pass in this sequence of words all at the same time. Encoder self-attention allows it to know where it should be paying attention to as it embeds each word, you know, kind of filling the role of that hidden state in an RNN, but in a more flexible and powerful way. Then you have positional encodings. And so like when you use an RNN, you're feeding in words one at a time. And so the position of that word in the sentence is baked into the RNN architecture. You don't have to tell the model, this is the first word, the second word, the third word, the 10th word in the sentence, because the model knows that, because you're passing the input in token by token. Whereas that doesn't happen with a transformer. Like you're passing in the whole sequence at the same time. And so you have to tell the model, this is the first word, this is the second word, this is the fifth word. And you do that with positional encodings. And so we're going to talk about how it does that. And then we're going to talk about like what I've called add and normalize, which is going to be really reminiscent of what we saw with ResNet, and is going to be important for why you are able to, you know, if you're OpenAI, why you can stack 96 transformer blocks on top of each other and not have a vanishing gradient problem or other problems. Okay. So I'm going to start out by talking about how we compute self-attention and what that means. And so as in the previous models we've seen, the initial inputs to the transformer are word vectors from a lookup table. And you know, that giant kind of lookup matrix, you know, say, you know, each of those has a certain dimensionality, you know, each of the word vectors could be 1024, like what the dimensionality of that is. Again, that's a choice, and it's going to depend on the size of your model. And so you have kind of those word vectors for each word that are themselves, you know, parameters, and you look those up, and you feed those into the model, and you feed them into the model, Again, central thing about this model, you feed them in at the same time, not sequentially as you would in an RNN. And so the first step to calculating self-attention is to compute 3 different vectors: a query vector, a key vector, and a value vector. And these are just calculated by multiplying the embeddings that are fed into the model by 3 matrices. And one thing to note is that these vectors have a lower dimensionality than the input vectors. And so in the transformer paper, the input word vectors are size dimensionality 512. And then these, key, query, and value vectors have size 64. And the reason for this, as we'll see in a few slides, is that the transformer has multiple attention heads, and this is done for computational purposes. Okay, so I want to kind of show this in figures, which are again taken from this blog post that I mentioned to you guys. And so let's say that we're going to feed in, just a two-word sentence, okay? So it will all fit on the page. And so we have 2 words, thinking and machines. We need to, and this is going to be a simplified version of what's going on to focus on self-attention. I'm going to, when after we see the different pieces, we'll kind of put it all together. But this is to show you guys how self-attention works. So we have 2 words, thinking machines. We look up their embeddings. In practice, that's going to be 512, but here, they're shown with 4-dimensional vectors. And then we have these matrices, WQ, W, which is the query matrix, WK, which is the key matrix, and WV, which is the value matrix. And we multiply those matrix multiplication to get a query vector, a key vector, and a value vector for each token in the input sequence. And those, as I said, are lower dimensionality. So maybe the inputs are 512 and those are 64 dimensional, but that can vary, just it's an architectural choice. And so we do that, and that gives us for each, and we've done this in parallel. We feed in all these words at the same time. In parallel, we multiply them by these weight matrices. And that gives us, for every token that is fed into the model, a query vector, a key vector, and a value vector. And those W matrices, those are estimated model parameters. Oops. Okay. And so just as with regular attention that we saw earlier, we use the query and the key to compute the attention scores. And so if we're talking about the word, the attention scores for the word thinking, its query vector is Q1. And so to get how much thinking should pay attention to itself in being embedded, we multiply Q1 times, or we take the dot product between Q1 and K1. Next, we want to know how much, thinking should pay attention to the word machines in creating its embedding. So we take its query vector, which is Q1, and multiply it times K2. If we were doing the same thing for machines, it would be Q2 times K1 would tell us how much machine should attend to thinking and creating its embedding. And Q2, which is machine's query vector times K2, is how much it should pay attention to the word key in creating its embedding. And so if we do this for each word kind of across the sequence, so here it's 2 words, in reality it might be 512 or more words. Okay. And we just compute that attention score, which is the number down there, with the dot product. And next, we divide the score by the square root of the key vector dimensionality. And so in the transformers paper, the key vector dimensionality is 64, square root of 64 is 8, so we divide by 8. And this is just kind of a technical detail that helps give us more stable gradients. And then we take the softmax, and as we might expect, the word at the position under consideration in this example has the higher score, but we're also attending to other words. And so these softmax scores are telling us, well, you know, in embedding thinking, we're mostly going to pay attention to that specific word. But we also want to pay attention somewhat to the word machines. Okay. And so next, we are going to multiply the softmax score times the value vector for each position. So you see there, so this is the example for thinking, and there's a value vector V1 that we multiply by 0.88. And then we're going to multiply V2, which is how much the value vector for machines, by 0.12. And you can see here kind of in this example, the softmax times value is fainter for the word machines, and that's meant to symbolize the fact that we're not paying as much attention to machines as we are to thinking and computing the output score for the word thinking. And so what this does is it preserves the values of words we want to focus on, and it will send the values, those blue vectors, of other words to 0 by multiplying them by a small number. And then finally, we add those up and those weighted values. So here Z1 equals the weighted sum of the value vectors for V1 and V2, where those weights are the softmax scores. And then we move over, you know, and then we do this again, we're doing this in parallel kind of for all words in our input sequence. And each of those words in our input sequence are going to have this Z score, which, you know, is the weighted sum of the values where the weights are the attention scores. And this produces the output of self-attention for that position, which is called Z. And so, you know, to write this in matrix format, again, remember this is going to be done in parallel for the entire sequence we pass in. We no longer have this sequential structure from an RNN. So again, suppose we have this, you know, simple 2-word example that we're passing in, you know, thinking machines, and we've represented those 512 vectors as these 4-dimensional vectors. We multiply them by the query matrix to get the query for each of those input tokens. We multiply them by the key matrix to get the key representations. And there's a key representation for each input token, and we multiply them by the value matrix to get the value for each of those, which are these lower dimensional vectors. We just compute those by matrix multiplication, and then we compute the z's, which you could just write as this formula, taking the query vector times the key vector, doing that normalization by dimensionality, and then, you know, taking the weighted sum of the value vectors, and that gives us the attention scores Z for each input word. And so I've shown you what a single attention head looks like. In reality, the transformer paper uses 8 attention heads. And again, that's like an architectural choice. And the reason it's using multiple attention heads is just to allow for multiple representation subspaces, which is going to lead to better results. So for example, you could have one attention head that's mostly paying attention to itself. Another attention head that's like paying attention to the noun that the pronoun refers to, you know, another attention head that's helping you to like paying attention to the word that helps you to disambiguate like what noun the pronoun should be referring to, kind of, and so on and so forth. Okay, and so, you know, this is a figure showing that, you know, this is just showing 2 of the heads, and for each head, it's a separate kind of independent W, Q, W, K, and WV matrix. And, you know, so in reality, you have like in the model, you have 8 of these. And so this is going to yield 8 different output vectors, you know, where there's an output vector for each token you feed in. So Z0, Z1, to, you know, to Z7. And recall that these representations are different dimensionality than the inputs. And so, you know, in the transformer paper, they would be 64 rather than 512. And so we can condense this, you know, into a single vector for each input because our feed forward layer is not expecting like 8 input values. It's expecting an input value. We condense this into a single vector for each input by multiplying by yet another matrix. And so that's going to, you know, combine these attention scores from the 8 different attention heads into a single vector for each input token, and its dimensionality is going to go back to the like 512 dimensionality, which is why we're going down to size 64 for these internal ones. And so you take it back, and now your final output from that self-attention layer is a vector that is the same dimensionality as your input, but that has, you know, attended in this sort of complex way to other parts of the sequence that you input into that self-attention head. So just to put it all together, we have this, you know, we start with, you know, a sequence that we want to input. So in this example, we call it thinking machines, and we embed each word by looking it up in a table. And then we split into 8 attention heads, and we multiply that input. So if it's the first layer of the encoder blocks, it's going to be, you know, the embeddings for the words. But at the subsequent layers, remember this is like 8 layers deep, it's just going to be the output of the previous block, which is going to be also a representation of the same dimensionality. So we're either feeding the embedding for the original words, or we're feeding the output representation from the previous block in, and we're multiplying those by the query and the key and the value matrices, which give us query, key, and value vectors for each token of the input. We use those to compute the attention score Z for each token at each head. We concatenate all of those and multiply them by another matrix to compute the final representation Z. Then that's going to go to the feed forward layer and circle back around to be the R that gets fed into the next layer. And so that's kind of the sum up of how encoder self-attention works. And so, you know, we saw before how this helps us to know where to pay attention to. Okay, are there any questions at all about encoder self-attention? Okay, and so there's another thing that we have not covered yet that's important. And so, you know, going back to the point of comparison with an RNN, the architecture of the RNN, the sequential architecture bakes in the order of the sequence, you know, like I am a student, you know, first you feed an I, and then sequentially you feed an am, then a student, like, and so you don't need to tell the model the order that the words appear in that sequence because you fed them in sequentially. Whereas kind of the, you know, key part of the innovation of the transformer is that you feed the entire kind of sequence in at the same time. And so now it's no longer baked into the architecture what the order of that sequence is. And so you have to tell it, you have to have a way to tell it the order of the words, because it needs to know that. Like you're gonna need to attend more probably to words that are nearby than to far away words. Like understanding the order of words is obviously kind of important to understanding language. And so the model addresses this by adding a vector to each input at the beginning of the model. And these follow a specific pattern which the model can learn in order to be able to incorporate positional information. And so you see that here. So this is kind of the first encoder block. And so you have your words, you look up their embeddings, but rather than passing those embeddings into the model, you add what's called a positional encoding. And the result of that is what you pass into the model. And you do that kind of at the first layer. And so this is an example, for say we have this input, and we're adding this positional encoding to each of the word embeddings. And this is like a plot of what the positional encodings look like. So this is from a transformer to transformer implementation package. And it's just plotting kind of, on the x-axis is the vector, like the 512 dimensional vector that you're adding on. And then the y-axis is just the order in your sequence. And this is like the plot of what it looks like. And you can see it kind of looks like two things stacked on top of each other. And that's because it's using like a sine and cosine function. In the original paper, they actually intersperse those like sine and cosine signals to look like this. And so kind of the details of this are not important. People do like positional encodings in different ways, but the key thing is that you have, a vector that is the same size as your input vector that you looked up in that word embedding table, and it follows a kind of a format that allows the model to learn the position of each word that you've passed in. Okay, are there any questions about positional encodings? Okay, so a third key component of the architecture is residual connections. And so, in the simplified figures we had so far, we didn't show this, but in reality, the paper uses both residual connections and normalization. And so, you feed thinking and machines into the self-attention layer, that gives you those outputs Z, but before you actually send those to the feed forward layer, you add them back to X, like your embeddings, and then you normalize everything so that you keep the scale the same as you move through kind of many layers of this network. And then you feed forward, and again, you add and normalize, right? And that's why we needed the dimensionality of that Z output from self-attention to ultimately be the same as the X that was fed into it. And so this looks an awful lot like ResNet, where you also have these add connections and you have normalization, throughout a very deep network. And so this is a theme that doing this helps you solve vanishing gradient problems and helps you, keep the values on a constant scale as you propagate through a very deep architecture. And so this is just another representation of that, where you feed in your embeddings for thinking and machines, you add them to your positional encodings, they go into the self-attention layer. The output of that is the two attention vector Z that we saw. You add Z to X, you normalize, and then the result of that gets passed into the feed forward layer, and then you just add and normalize again. Okay, so that is the encoder blocks. Does anyone have any questions about how the encoder blocks work? Okay, So now I'm going to move on to talking about the decoder blocks. And if you've understood the encoder blocks, the decoder blocks, you're almost there with the decoder blocks, but there's just a couple of things that need to be noted. So this is, this is showing the architecture, and you have your decoder there on the right. And in many ways, it's similar to the encoder, but the thing that is different is that you have kind of this additional layer that you've sandwiched into the decoder. So in addition to the self-attention block, there's something called the encoder-decoder attention block. And so that's one difference. And so now instead of having self-attention and a feed forward layer within each block, like you do in the encoder blocks, within each decoder block, you have self-attention, you have encoder-decoder attention, and you have feed forward. And the encoder-decoder attention, as the name kind of insinuates, is going to let you pay attention to the encoder, much as we saw in the seek-to-seek model at the beginning of class. And then the other thing that's different is that the self-attention blocks are going to be somewhat different than they are in the encoder. And so encoder-decoder attention allows the decoder blocks to attend to the hidden states from the last layer of the encoder. And this is kind of analogous to kind of the attention that we saw in seek-to-seek at the beginning. And so in addition to having this self-attention where the input sequence attends to itself, and that's kind of replacing the sequentiality of the RNN that we saw with seek-to-seek, we also have the, attention here where the decoder is paying attention to the encoder. And so specifically what happens is you have the key and value outputs from the top encoder, and they are used by each encoder-decoder attention block to help the decoder focus on appropriate positions in the input sequence. And so here, at the first stage of the decoder, you start it with a start token, and you're passing that through these multiple layers of decoders, and you get the output I, and then that becomes your input at the next stage, and you're passing am, a, student, in sentence. And so notice here that kind of sequentiality has came back. You're not passing, everything into the decoder at the same time, because the point of the decoder is you're predicting the next word, and then that next word is your input. So this continues sequentially until an end token is reached, and is kind of analogous to how attention works in the vanilla seek-to-seek attention model that we saw. And it's also like analogous to how the self-attention blocks work, except that the key and value vectors come from the last encoder layer, and the queries come from the layer below in the decoder. But besides the fact that you're getting, those key, the vectors that you need to compute it from the encoder layer, the computation is analogous. Key and value and query vectors mean the same thing. And the decoder blocks, they're just coming from someplace different. Okay, so is kind of encoder-decoder attention clear what that means? Okay, and so, that's relevant for understanding the transformer sort of for machine translation. But when we talk about language modeling and we're only using encoder and decoder stacks, like the language models that use stacked decoders are actually going to throw out that layer, right? Because if you're just stacking decoders, there's no encoder to attend to. And the key difference between using kind of the encoder or the decoder side comes down to how attention works in each of them. And so in the encoder self-attention blocks, a position can see tokens from both sides, from, if we're thinking about how things are written in English, it can see tokens from both the left and the right. We feed in that entire sequence and it can attend to any token that it wants in the sequence. Whereas this is not the case for the decoder. For the decoder, when we're training it, we're still going to feed in, the full sequence in parallel, but we're not going to let it see subsequent words that are ahead of it in the sequence. And the idea here is kind of akin to predicting the next word, given the previous context. And so you see in this figure, with self-attention at a given position, you can attend to everything in the encoder, but in the decoder, it's only letting it attend in training kind of to those previous contexts. And the point of the decoder is to predict like what comes next. So let's just recap self-attention without masking, where you can pay attention to anything like it worked in the encoder. And so for each input token, we create a query vector, a key vector, and a value vector by multiplying by the WQ, WK, and WV matrices, which consist of estimated parameters. We take the dot product of the query vector by all the key vectors to get a score of how well they match. Then, essentially we multiply those by the values and add those up. And, we do that for each input token to give us these self-attention scores for each input token. And so mass self-attention, which is what we use in the decoder, is exactly the same, except at step 2, which is where, we're computing those attention scores. And so now we don't allow a token to attend to future tokens in the sequence. We only allow it to attend to the previous tokens. And so how do we do that in practice? Well, suppose we have a sentence with 4 words and we have a target sentence with labels where we're trying to predict what comes next. So we calculate the attention score by multiplying the query matrix by the key matrix. And so, it's shown in this figure using just words, but in practice, each word is associated with a vector, right? And so when we multiply the query matrix times the key matrix, that gives us scores. We haven't softmaxed those yet. So you can see we're doing this just like we did at the encoder stage. We're asking how much a given token should attend to every other token in the sequence. But then we take we apply an attention mask. And remember, we're gonna softmax. And so we just, essentially multiply by 1 for everything that it's allowed to attend to. So itself and all previous words. And then we set attention score for all future words to negative infinity or some very large negative number, right? And then we softmax that, which means the attention score for every future word in the sequence is going to be 0. And yeah, that's it. And so now we're not attending at all to the future words. And so basically we compute it just like we compute encoder self-attention, but we just have this additional mask that we apply that effectively sets the attention scores to 0 for any subsequent words in the sequence. Hence, we are only attending to the previous words. Okay, are there any questions at all about the decoder? Okay, so I'll say just a word about the linear and softmax layers, which are really straightforward. And so, our output from the decoder is a vector. How do we turn that into a word? Well, we do that with the linear and softmax layers. And so the linear layer is just a vanilla fully connected network that projects the vector produced by the decoder stack into a much larger vector called the logits vector. And so, the decoder may produce this, depending on the dimensionality of your model, maybe it's, like a 564 dimensional vector, but we need to project that kind of into, it's a very like dense vector. And we're gonna project that into a much larger vector, into the logits vector. And the size of that logits vector is gonna be the number of words in your vocabulary. So if you have 10,000 words in your vocabulary, the logits vector would have dimensionality 10,000, with each value corresponding to the score of a unique word. And then you softmax to turn those into probabilities, and the cell with the highest probability is chosen, at least if you're using greedy decoding. If you're doing beam search, you may keep track of more than one. And that's it for, this is just a vanilla fully connected layer that's taking us from those dense representations into a probability for each word in our vocabulary. Training is straightforward now that you've kind of understood the details of the model. And so our training objective is just a cross entropy loss, like we saw before. And so, this, we know what our target sentence is. So, that puts, a 1 on that and a 0 on everything else. And then say this is our model output, and we just, take the difference to compute our cross entropy loss. Now, kind of in reality, instead of doing greedy decoding, usually people will do beam search decoding. And so just to recap, at each step, we keep track of the k most plausible partial translation, so which we call hypotheses, where k is the beam size. So it would be kind of standard to have k be like 10. And the plausibility score is just the probability of that sequence, which you get from the softmax outputs. And when a hypothesis produces the end token, you put it aside and you keep on exploring other hypotheses until either you reach a given time step, or once you've collected at least n completed hypotheses, you normalize the score by the length and then select the final hypothesis that is the most probable. And then you would compute your cross entropy loss. Okay, are there any questions about training? Okay, and so now you guys have seen the transformer. Definitely kind of be sure to understand it before next class, because on Wednesday we're going to be talking about different language models that use the transformer in various ways. And then kind of the rest of the class is talking about how we use the representations from those language models to do downstream tasks. And so one downstream task could be classification. So you're classifying the sentiment of something or the topic of something. Another downstream task would be, named entity recognition, part of speech tagging, dependency parsing that we talked about, or it might be query, trying to find relevant information. It might be summarization. And so essentially we're going to talk about a bunch of different downstream tasks that you guys ultimately want to be able to do. But the basis for all of those downstream tasks is to have a representation of text that allows you to perform the downstream task accurately. And in modern NLP, pretty much all of those, models, language models for creating those representations use the transformer in one way or another. And so next class, we're going to talk about the different options for language models that you might choose to use in their architectures, and talk about kind of how they use the transformer and also other kind of important practical details like the type of data that they're trained on. And so kind of be sure to understand everything that we've gone over today. All right, thank you.